All right.
So we're going to talk about feedback-directed optimization in
as opposed to the previous slides, we haven't done anything about this yet. I want to tell you the first 2 minutes what we've done in the past at Google. We are obsessed with optimization. And we're obsessed with performance, of course, of our own internal programs. And we found over time that the real benefit for optimizations that we obtain is in feedback-directed optimizations. We get, by just applying FDO to the options, we get about 7 to 10% optimization. If on top of that, we do whole program optimization, and in particular, cross-module inlining, we can get up to 30% more. This is an optimization called LiPo, which stands for, what was it? Lightweight Intra-Procedural Optimizer. It's essentially inlining across modules. When the program is built with feedback optimization, when it runs, the functions from different files that are found to be in a click are then compiled on the second compile, they're compiled together. And so the inliner puts them together, and that's how we get the core optimizations. And we also tried the traditional LTO, which GCC being GCC didn't cooperate with us. And we spent most of the time fixing architectural issues in GCC. So this way, but however, once that was done, LTO itself, just looking at the whole program, doesn't actually help. The folks who worked on LiPo found that if you look at the, say, 10% of the nodes that are communicating heavily in the program, you get this 30% speed up. If you look at more nodes, you get the same 30% speed up. So in a sense, LTO is useless because you're looking, 90% of the stuff you're looking at does not help you. And that's why feedback for us is so important. Inlining, code layout, register allocation are the main beneficiaries of FDO. However, using FDO is hard. The usability model of FDO, the traditional FDO, you build a program with this instrumentation, then you have to run it, the instrumented program, you have to run it with representative inputs, and then you compile it again. And so you have two tricks. You have to compile your program more than once, you have to find the representative inputs, and you have to put all this burden on the user. Some users don't care, and other users, most of them, they really do care. And they won't do it because they say, 10% is not the price I want to pay for all this build pain. So at Google, we have a build environment that simplifies, makes it somewhat easier, but not enough that we get a lot of use internally. We do get a use from the usual suspects. So what we're really striving internally, and there have been several projects over the years, is for a simplified model. And one of the things that we're moving towards today is something called Auto FDO, in which you essentially have no training runs. The program running, like the usual run of the program, you make it collect profiles via sampling, hardware counters, what have you. So you have a profiling source that's always enabled while programs run. And what happens is you get this loose profile of the program execution that then you use when you compile. So ideally, this is transparent for users. Their program runs normally. The hardware counters emit sample information. Couple that with the debug information. When you go and compile again, you use this loose profile from the program to optimize it, in the hopes that you'll get close to the instrumented model. So this is something that we can turn to users and say, flip this magic bit on your build files, and it will happen for you. It's getting there. The performance of the automatically done FDO is a fraction of the instrumented FDO. And so we are thinking that we can, in bringing this technology to LLVM, we're trying to bring the auto FDO technology. That would be the initial plan. There's a thought that we may need to also do instrumentation to get the real peak benefits, and that's all I'm going to say.
Going to take another minute.
Okay, so that was essentially it. We were going to try to go for the automatic. We're going to add instrumentation and tie it to the LLVM analysis and see. We got to see what, as Chandler pointed out yesterday, apparently inlining is going to be one of the things we have to look at. I'm done.